Hi people, so let me give you guys a story. You know when you wake up and you check your phone battery, oh, you check your phone battery, it's on 4%, right? So you put it on your charger and you go get ready, and it takes you about like 25 to 30 minutes to get ready. So you go back, you're about to take your phone and go to work or wherever you're going, you check the phone battery, it's on 6%. You're only on 2%. What's happening here? And you're thinking to yourself, damn, I don't want to pay for a new phone. I don't want to pay for a battery replacement. So what am I really gonna do? So introducing fast charging lithium-ion batteries. So let's show you around the lab. Come here. So this whole lab is wonderful. It's a wonderful experience. You know what I'm saying? And over here is our general station where I work at. Let me welcome my co-worker right here. How you doing?
Hi. Nice.
So are you a satisfied customer of our batteries, of our fast charging lithium-ion batteries?
No. Why?
Let's keep going.
Okay.
So this is our workstation. This is where all the magic gets done, you know? So what battery specifically is the one that charges quicker, you ask? Well, let me tell you something. It's lithium manganese oxide. So the magic that specifically happens in this lab is preparation of lithium manganese oxide and lithium titanium oxide batteries. So what happens is that we have specific chemicals over here. So this is the actual, let's open this up. This is actual LMO powder imported commercially, you know, has this amazing structure. And what allows LMO batteries to have this fast charging capabilities is the spinal structure of LMO. It's amazing. It's great if you ask me. So what do? Well, first, to make a battery, we have to make something called a slurry, where it is a combination of this active material, because this is where the redox reactions happen, along with this PVDF in NMP solvent. NMP is a very widely known solvent, and this is more just NMP in here. So we combine that all in a certain mass ratio to form this kind of slurry that kind of looks like this. Has very black, yogurt-like solution type mix. And same thing we do for LTO. Now, why do we use LTO? Well, typically when batteries are made, we make a certain electrode with respect to another counter electrode. So for example, if I'm making a half cell, an LMO half cell or LTO half cell, I always put them with respect to lithium metal. And why is that? Because lithium metal has a very low working potential. Now, LTO, on the other hand, has a pretty high energy density and has a pretty relatively high working potential of around 1.5 to 1.7, which is why we use LMO to LTO, because we want high energy density to increase performance of our batteries. So the same process goes for LTO. We're making the LTO slurry. We, instead of LMO though, we use lithium titanium oxide in this box right here. And we just combine them up with PVDF as well, NMP, and also one more thing I forgot, but this carbon, but it's not just carbon, it's electroconductive carbon black. It's a very special type of carbon. It's electroconductive. So now, what do we do when we have these slurries? Well, we have either aluminum mesh, copper mesh, or aluminum foil or copper foil. Those are used as current collectors. And what do? They collect current. So what do? So here in the dryer, after we produce the slurry, we take the mesh and we coat it. We coat the slurry onto the mesh like so. And we leave it in the dryer overnight so that all the NMP solvent, because it's a solvent, evaporates out. And then we just get on the mesh an electrode, literally an electrode that we can then put into a cell and actually have, and actually get batteries out of it. And we basically, what we do after we get that, we punch holes out of the electrode using this fancy machine by the name of a hole puncher. And then we walk over into the glove box right there. Let's take a nice fancy walk. No! We can take a nice fancy walk over here, and our coin cell assembly happens right in here in this magic box. And if you could show it right there. Yes, that stuff. And then at the end, what happens? Well, we get something fancy like this coin cell right here. And you can actually measure the difference in potential between the two terminals and get a good result. So essentially that is the holy grail of what's happening in the slab, and obviously there are other measurements taken as well, such as the capacity of the battery, which depends on the mass of the active material. But in terms of practicality, this is the main things that we do here. Welcome to TMD Lab.